Well, congratulations, you've almost made it. Almost. Welcome to our last lecture, Lecture 8, in which we are going to talk about quantum error correction, how to deal with quantum noise, how to recover quantum states and protect our precious quantum computations or quantum communication. It's been a long journey. We started with 4 introductory lectures where I introduced some basic stuff for you to understand why quantum information processing is more powerful. So we talk about quantum interference, we talk about quantum entanglement. And then we could see how quantum interference and quantum entanglement play a significant role in making quantum communication secure or computation more powerful. But we also observed that the reason we do not have, for example, quantum computers yet is because quantum systems, or quantum interference in particular, is quite fragile, right? So you expose it to any interaction with the environment may learn about the state of the system, and quantum interference is gone. So we took some time to describe the system environment kind of interaction. So that is the dynamics of open quantum systems. Our quantum computers or quantum communication devices are open quantum systems because even though we can control them to some extent, they're embedded in some sort of environment upon which we do not have complete control. So it's not quite right to describe the evolution of open quantum system as a unitary evolution. We know that you can take 2 approaches here, right? So you can think about a unitary evolution of the whole when you include the environment. That's the so-called Stein spring representation. But you can also look at the system alone and analyze the evolution of such system in the presence of the environment, but not necessarily just including the environment in your equation. So that's the Krauss representation. Now, we have the tools, so we can now move on and discuss how we can deal with quantum errors. So whenever, remember, we call Krauss operators quantum errors, but the question really is, so given a system that undergoes some sort of evolution described by a completely positive map, is it possible to recover the original state of the system? So I would like you to have this kind of scenario in mind. So compare the 2 cases. The case where we have a system, let's say it's a qubit. You can always choose the simplest possible quantum system. So we have a qubit. This qubit undergoes decoherence, so interacts with the environment, and as a result, the state of the qubit is modified in some way. Now, is there a way to diminish the impact of the environment? And here we are going to borrow ideas from classical theory of information. So we are going to use the concept of error correcting codes. So instead of this kind of scenario, we are going to encode the state of the qubit into a number of qubits. So we are going to bring a few more qubits and take our original qubit, and we are going to perform a unitary operation that maps unknown state of the qubit into a set of qubits that will form our encoded qubit. So this, mathematically speaking, we are just going to pick up a 2-dimensional Hilbert space, and we are going to embed it in a higher dimensional Hilbert space, rotate somehow. That's isometry, right? So that's going to be the encoding part. And then all the qubits go to the decoherence area. So errors will appear. And then at this point, you may be a little bit confused. You say, okay, well, now the errors will appear on many qubits. Well, yes, but if you just take quantum state of one qubit and somehow spread this state number of qubits, then the error on one qubit may not perhaps be so significant. It may be possible to recover it under certain conditions. And indeed, we will see that under certain conditions, it is possible to recover, to reverse this completely positive map. So the first one, the errors are induced by the environment, which you cannot control. But as long as you can find out roughly what happened, then you can then just apply another completely positive map. In this case, we don't have the environment, but we just bring extra, even more qubits or some other quantum systems, auxiliary qubits, or a system that we call ancilla, a kind of a helper to help us to perform in a control way another completely positive map. So that's going to be error recovery. And then once hopefully we manage to recover the original state of all those qubits, then we just simply decode the quantum state. So we just map the state into the qubit, and hopefully we'll have something that is very close to the original. So I would like you to have this scenario in mind, and of course, you know, in the lecture we will go through all the details, and I'm going to tell you how to encode, how to construct the recovery procedure, and how we are going to, what kind of conditions have to be satisfied for this to be possible in the first place. Then we'll say a few words about quantum computation that protects about a way of computing that you protect not only a quantum state but also the whole process of computation. So you'd like to have your evolving state modified by your quantum logic gates protected at all time. Well, so this will essentially actually conclude our basic introduction to quantum information processing. It should give you some sort of simple but complete picture of how things work.